Hi! In this video, I will show how you can get started with IoT using a Raspberry Pi. We will read values from 6 different sensors connected to the GPIO pins on the Raspberry Pi and also get some values from an Arduino. We will then do some processing on the values using Python inside the Raspberry Pi and then push the values out to a Mongo DB database, Thingspeak cloud service, and also an online MQTT broker. So let's see how all this is done. Before we begin, I just want to mention that a prerequisite to this video is to have Raspberry Pi operating system installed. So if you need help with that, you can check out my previous video in the link below. To give an overview over the system we're going to make, I have splitted the system into 3 parts. On the left side in the diagram, you see all the electronic devices. Here we have 3 different temperature sensors using different communication protocols, and we also have a light sensor, a potentiometer, and an LED and a push button. When looking at the circuit, it may look messy, but it's actually just several smaller sub-circuits which are not interconnected at all. So this will be more clear when we go through every one of them in just a minute. The second part of this diagram contains the Arduino and the Raspberry Pi. The only reason we are using the Arduino here is because it has analog input pins. The Raspberry Pi is the most important part in the project because it's the only part that all the data flows through. Its job is to read all the different protocols, collect the signals together, and push the data out. The third part of the diagram is the data destinations, where all the collected sensor data will be stored. In MongoDB, we will create a database made specifically for time series data, and in the end create an application that can view this data, plot it, and also do some statistical analysis. Let's start at looking closer at how the Raspberry Pi is configured. Right now, the Raspberry Pi is connected to the local Wi-Fi inside my home network, and so is also my computer, and that allows me to connect to the Raspberry Pi using this real VNC viewer. Using this, I can write in my IP address and my username and password, and I get the Raspberry Pi desktop in front of me. If you are not able to do this, the cause might be that you don't have the VNC enabled. In that case, you can go into the Raspberry Pi configuration section and enable some features. If you go to the Interfaces tab, you should check that the VNC option is enabled. In addition, you should also enable the SPI button and also the I2C, because these two will be used for the temperature sensors later in this video. Python comes pre-installed on the Raspberry Pi, so we are almost ready to start coding. But before that, we will create a Python virtual environment, which is a separate environment that allows us to install more libraries without interfering with the complete Python installation. So to do that, we first need to decide where we want to place this new virtual environment. I have decided that I want my virtual environment inside my documents folder. So to create it, we will start the terminal, and first we will navigate to the folder using the cd command. Then we create environment by entering python 3 -m venv and then the name of the environment. I will just use IoT env. When pressing enter, you see that the files appear here, and the files inside the folder are the files used to run the environment. So for example, this is used to activate the environment from the command line, and Python 3 is used for starting the environment. In the terminal, we can now activate the environment by entering source, IoT, the name of our folder. We can use tab to autocomplete, then bin, and again we can write AC and press tab to get activate. Press enter, and we see that we have enabled the environment because it's indicated by the text in front of the line. So now we can install any library from the terminal, and it will only exist inside the virtual environment. For programming on the Raspberry Pi, I like to use the Tony editor, and we also need to enable the environment inside this. To do that, we can go to the configure interpreter, and we need to navigate to the correct Python executable inside the documents folder, IoT environment, the bin folder, and go to the Python 3 executable. Press OK, and we are now ready to start coding. The first sensor we will get working is this blue sensor for humidity and temperature called DHT11. It has only one signal wire connected to the GPIO pin 4. It also has a pull-up resistor of 10 kilo ohms. To use it, we need to install the Adafruit CircuitPython DHT library. And when that's done installing, we can run some code. In the code for reading this sensor, I first import the library we just installed and also the board library. And I have created a class where it first initializes the sensor by connecting it to the D4 GPIO pin. And then I have defined a function that is reading the temperature. The only thing it does is to use the sensor.temperature and get the value from there. So when using this class, I first create an instance of it, and then I call the getTemperature function to get the temperature. Then I print it to the console. So you can see that when I press it, I get the temperature of 19. And sometimes I get an error, but this is common for this sensor. But as you see, this is working as it should. So that's it for this sensor. The next one is the TC74 temperature sensor using I2C. The TC74 sensor is this one with 5 legs, but we are actually using only 4 of them, 2 for power and 2 for the I2C signals. The SDA pin is connected to GPIO2 and the clock pin is connected to GPIO3. To see that the sensor is connected correctly, we can use the I2C detector inside Linux. As you see, the function returns one value inside this table, which means that our sensor is connected correctly and have the ID of 48. To get this sensor working, we also need to install another library, which is called SMBus. In the code for this sensor, we first import the SMBus library, and in the initialize function, we use the same address as we found earlier for the sensor. In the read function, we read data from the correct address and the correct register inside the sensor, and we get some data. This is then converted to allow negative values, and the temperature is returned. This class is used as usual by first initializing it, and then we call the getTemperature class to get the temperature, which is then printed. When we test it, you see that we also get the value of 19 degrees Celsius here, so this is also working correctly. The next sensor is this TMP36 temperature sensor. This is an analog sensor and it gives out 0.5 volts at 0 degrees Celsius. For each degree above that, it gives out 10 millivolts extra. And because the Raspberry Pi is not able to read an analog voltage, we need to convert the signal to a digital using an AD converter. For this, we will use the MCP3002 converter, which is connected to the Raspberry Pi using SPI. This ADC converter has 2 pins for power, 2 analog inputs, but we are only using one of them. And it also has the 4 wires used for the SPI signals. For this sensor, we need to install the SPI dev library. The code for this works as usual by importing the library. I initialize some values in the init function, and inside the read function, we read in the register and do some bit slicing and shifting to get the values correct, and then we return that voltage. But when you use the class, it works as usual by initializing the class and calling the getValue function. When I run it, you see it returns a temperature value of 17.99 degrees Celsius. So that's it for this one. On the circuit board, we also have this LED and this push button. The LED is connected to GPIO 12 and is connected in series with a 200 ohm resistor. The button is connected to GPIO 5 and has a 10 kilo ohms pull down resistor. As usual, we need to install our library to use this, and this time we will use something called pgpio. So we can install this the regular way, and by the way, this command prompt is also a part of the virtual environment. In the button and LED code, we first define the pin numbers and initialize this Pi object. On the button, I set the mode to input, and for the LED, I have created a function used to set the brightness of the LED. Because the GPIO pin we have connected the LED to is a PWM pin, we can control it from 0 to 100%. Right below, you see that we use this here. So we put in the pin number, and the percentage of how bright we want it to be. We also read the button state, and we can print it out so we can see the state. When I now run it, you see that I get the one error code, and it asks me if I remembered to start the Pi GPIO daemon, and I forgot that, so we will do that right now. I just open another command prompt and type in sudo pi GPIO d. Now we can try again, and I see immediately that the LED is emitting light, and you also see the button state is 0. If I hold down the button while I run the script, you see that the print statement prints out a 1. If I now change the brightness of the LED from 20 to 100, we see that the brightness increases as expected. That's all the electronics connected directly to the Raspberry Pi, but we also have some data coming in from the Arduino. To the Arduino board, I have connected this LDR and a normal potentiometer. The potentiometer is connected to A0, the first analog input pin on the Arduino, and the LDR is connected to A1. That input is taken from the middle of a voltage divider using a 2 kilo ohms resistor. To transfer this data to the Raspberry Pi, I used the USB cable and the serial port, and there's actually a very simple code inside the Arduino which only is reading the values and sending it out on the serial port. The data format it sends looks like this. It puts the name of the sensor equals 22 and then a tab character, and then the same for the next sensor. So it is just continuously sending these lines. The first thing we have to do is to check which serial port the Arduino is connected to. So before I connect the Arduino, I run this command ls/dev tty*, and here I get the list over all the currently connected devices. I now plug in my Arduino and run this code again, and we can see that we got one new device called ACM0. So this is what we will use in our Python code. As usual, I have made a class that handles all the logic for the sensors, and when I use it, I first need to initialize it, and there I use the port name of the serial port. I then later can use this instance of the class and use the getSensor to get sensor value from analog input 0 and from analog input 1. And you can see when I run it, I get value for the potentiometer and for the light sensor. I can, for example, cover up the light sensor and run it again, and you will then see that I get a much smaller value for the light sensor. The reason I use the time sleep here is to let the serial port buffer get some values before I would try to read it. If I hadn't done this, the serial port might be empty when we try to read it. We can take a closer look at how this class works. We have one initialize function that starts the serial port communication. We then have a function for opening the serial port, closing the serial port, and the most important one, process serial, and also one get sensor. Here, the process serial function is called first, and what it does is to move the latest values from the serial buffer to the variables for sensor 1 or sensor 2. One of these values are then returned. So that's all there is to this one. And of course there are also some exception handling. So now I have gone through how I interface with all the electronics. So now we can make this into a bigger script and read everything at once. In this project I had decided to use the Mongo DB database, and I wanted to install it on a Windows computer. You could also use it as a web service and have all the data stored in the cloud, but in my case I just wanted it locally on a computer. So I downloaded the install files for the version 7.0.7 and installed everything. I also selected to install this Compass program. That is a graphical user interface you can use to connect and do operations on your database. When you first open it, you can connect to your database by pressing connect, and you should see all the databases that you have here and also all the tables inside. In MongoDB, they actually call a table a collection, and a record in the database, as you see here, is called a document. And that's because it's actually like an object where you have a key and a value. So when you set up this database and you want it available on your network, you need to configure the settings first. So there is a file that you can find inside this folder here, which is a configuration file. And down here at the field called bind IP, under the network interface part, you can set up your IP address that you want to bind the server to. So that's usually the IP address of the server that the database is installed on. So now we should be able to connect to this database using this port and this IP address from the Raspberry Pi. The database we will use is inside this IoT DB, and we will use the collection called time test. This one, as you see here, has this line chart as a symbol, which means that it is a time series database. And that means that it is optimized for storing data varying with time, and it will therefore be faster to query than a normal database. So let's go ahead and make some code on the Raspberry Pi. Actually, before we write any code, we need to install the correct library. So we can open this system shell again, and we write pip install pymongo srv. In the code on the Raspberry Pi, I initialize my custom class to connect to the database with the database name, the collection name, and the IP address. We can then use the insert sensor data function of this object and later insert the data. In this case, I have just created some example data inside a Python dictionary, and for each line in the dictionary, I call the insert data function. So to look closer in the class I have made, we see that first the initialize sensor just takes some information. It then calls the connect function that connects to the MongoDB client, and then the insert sensor data takes the current timestamp and inserts that into the MongoDB database together with the sensor ID and the value. And we can run a quick test of this, and we see that it returns a successful send operation. We can also take a look at this inside the database. Inside Compass, type a query like this. I write in sensor ID because that's the column we want to filter on, and then the sensor ID. So when I press find, it sorts out all the items, and I have enabled sorting on timestamp, so we will find the newest values on top. So here we see the result. We have the value of 999 here, which is exactly what we wrote from the Raspberry Pi. The next step is to create a script that reads all the sensors and sends the data to the database. And that's what you see here. This script works very similar to the individual smaller ones, doing only one thing. But here I have combined everything. So I first import all the libraries, and below here I have copied in all the classes, which allow us to communicate with the devices. And in the Python main function, which is the first thing that's run, I have created an instance of each class. In addition, I have created a low-pass filter class that I also initialize to make one filter for each value. This is used to filter out noise if there's a very unstable signal. So here I have the 4 classes initialized, and also the one to communicate with the MongoDB database. I also initialized the LED and the button. For fun, I have also created an alarm that triggers the LED when the light is below a certain limit, and I initialize it to the off state. In the main section of the code, I start a loop, and every time I start with an empty data frame, which is the data we are going to send to the database. Then I call the get value from each of the sensor classes, and I also use the filter belonging to that sensor and send the value into the filter. I can then use the filter value, and that's the one I put into the data frame and which will be sent to the database. So I do this for all the sensors, and in the bottom you can see that this data is sent to the database. I also had to make some code for the alarm, which you can find here. This code checks if the light is below the alarm limit, and if it is, it sets the alarm state to 1. It then checks for a button press to acknowledge this alarm and remove it. And if it sees that the button is pressed, it sets the alarm state to 2, which means acknowledge. When the alarm is acknowledged, it is in a state where it has a lower brightness, and when the situation is then cleared and the sensor reads a high enough value, it will then automatically go back to the clear state with no light on the LED. So that's how the alarm section works. So now we can try it out. You see that it connects to the MongoDB successfully, and we start getting a lot of data. If we now go into the MongoDB database, we can press find here, and we see that we get new data continuously entering, And I can also remove this filter to see all the data. And here we see that we get values, for example, the Arduino light sensor. To automatically start the Python script that reads all the sensors when the Raspberry Pi starts up, we can create a bash script that does this for us. I have created that script here and called it launch.sh. Inside the script file, we first have the shebang line indicating that this file can be run as a script. Then we print out a string, and then we start our script by first referencing the Python version in our virtual environment, and then referencing the script file, which is the one that we are actually going to start. This is the Python script. And when this script is run, it will start the Python script and it will start collecting data. And I almost forgot, you also need to start the PyGPIO daemon in the script, so you should add these 2 lines. In the terminal, we have to change the permissions for this file to change it from being just a normal text file to become an executable script. I then enter sh and the name of my script and press enter, and we see that the data is flowing in. By the way, I can press Ctrl+C to stop this. Now, if we can get this to auto start when we start our Raspberry Pi, everything should be working fine. But when we configure this to run at startup, the difference will be that we will not be able to see its output. So for this, I just create a folder called logs that we will use later. Now we are going to add a script as a cron job, so type in sudo crontab-e. If you see a question asking what editor you want to use, just type in 1 for the nano editor. And now we are inside a file where we can specify jobs to be done by this cron job daemon. Type in this line starting with reboot, then sh, the full path of the script, and then we send the output data to a file called cronlog located in the logs folder. Just save this by pressing Ctrl X and press Y to save, and confirm by pressing enter. And I almost forgot, we also need to make a startup delay here. Just write sleep and then 60 and this ampersand character. Now we can try a reboot of the Raspberry Pi and see if the changes worked. Now let's check this logs folder that we created. And as you see, we have a file called cronlog. And as you see, we have a lot of data in this file, and what it contains is all the print statements from the Python script. So this file confirms that the script is running and working. We should probably reduce the number of print statements used in the file, but anyway, you understand the concept. We can also confirm that the script is running by testing our alarm functionality. If I hold over the light sensor, you see that the alarm LED lights up, and if I press this acknowledge button, you see that the color is dimming down and eventually disappears. So the script is running in the background. There's no point in collecting data from IoT devices if it's not possible to use the data further down the line. We put the data into a database, and that's a good first step, but we should also think about how we can make the data even easier accessible for people that don't have technical knowledge. I have created a very simple solution to this problem by creating this Python script. When I run it, it plots the temperature data for the last 10 minutes, and here you see all the 3 sensors. It also displays some statistics for the sensor, for example the standard deviation of each sensor, the average value, maximum value, and the minimum value. So with this simple script, it's easier to get an idea of what's happening to the temperature data. Another possibility is to send the data we have on our Raspberry Pi to Thingspeak. Thingspeak is a web service where we can upload data and display it as a time series curve. In Thingspeak you can define channels, and here I have made one for this project, and inside the channel I have made 5 different fields. These fields will store the value from our sensors. It's actually very easy to upload data to Thingspeak. You can use a normal link like you use in the web browser, and you use a special key that connects you to your own account. You then just specify what field you want to add a value to, and you write the value in the link. So that's it. When you use this, you will upload data to the cloud. I install the library we need for Thingspeak using pip install requests. This is just a normal HTTP request library. The example code for using Thingspeak in the Raspberry Pi is pretty simple. I'm using a custom function that takes the API key to Thingspeak as an input and also an array of the values we want to upload. Then it uses the library to do this, and that's all there is to it. To use it, you only use the function and put in the key and the array. Let's see if it works. Yeah, that's it. This code can easily be copied into the data collection script like this. In Thingspeak, we see that new data is coming in with values of around 19 degrees Celsius. You can then, for example, make your Thingspeak values publicly available and share it with the world, or read the data into some other software. The MQTT protocol has become one of the most popular protocols for IoT. This is because MQTT is lightweight, uses low network bandwidth, and uses a publish-subscribe model. When working with MQTT, I like to use this MQTT Explorer tool to view what's going on the server, or the broker as it's called. This program is free and I really recommend it. We are soon going to push some data from the Raspberry Pi up to an MQTT broker, but first we can connect to an online broker and see what it looks like. We are going to use testmosquito.org. When you press connect, we immediately see a lot of data coming in, and this is data published by others to this online public MQTT broker. And obviously there's no security when using this because everyone can see what you publish, but we will use this broker to publish the Raspberry Pi data, and we can then view it using this tool. We can see that others have organized their data into folders, and that's what we are going to do as well. So we will make a folder for our project and put our values inside. The MQTT broker is not storing any historical data, but if you want, you can subscribe to a specific MQTT topic and, for example, save that in a database. But we're not going to do that now. This is my example code for uploading MQTT data from the Raspberry Pi, and to use it, you need to install the Paho MQTT library. As usual, I have made a class that handles all the MQTT logic, and when using it, you first need to create the instance of the class and provide it with the broker address, which is the IP address or a host name. Then you also need a port, which is the standard MQTT port. And then you can use this object and use the upload function to push data to the online broker. The data is pushed into a specific topic, which you can send in as a parameter, and you also send the value. And this value will show up as a string on the broker. So that's it. Now let's copy this code into the data collection script. The only thing we have to change is the upload values line, which will be put inside a loop to go through each of the sensor values. When running the code, we see that the code prints that the values are published. So let's head over to MQTT Explorer to see them. There are a lot of topics here, so let's search for the top folder in the topic we are using. And here we see all the values. You can also see that they are constantly changing as the Raspberry Pi runs the script. And this data can now be easily used by other systems used to display it or to store it in a database. So that's all you need to get started with MQTT. In the end, I have a few words about cybersecurity, and I have split this into network security, application security, and data security. We are not facing any big risks inside the network security category because we are using a Raspberry Pi inside a local network and we have not opened any ports to the outside world in our router. However, if we are going to expose it to the outer world, we should make sure to have a firewall configured to only allow, for example, a specific IP address source, and also allowing only a few ports on the Raspberry Pi. But generally, the safest way for remote access of your Raspberry Pi is to configure a VPN, and that makes everything work as if you were on a private network. Application security is also important, and here you need to take care of things like updating the system, change both the username and password, avoid storing passwords in clear text, and also make sure that you don't create any other security holes with your application. For example, like allowing SQL injection attacks to happen. To maintain good data security, we should think about who has access to the data, and for example, avoiding publishing sensitive data to an online service, for example, like MQTT or Thingspeak. When the information is transferred, we should also make sure it is encrypted so it cannot be read by anyone else. And if you are using a web server, this can be done by switching from HTTP to HTTPS. So, if you're going to make a Raspberry Pi system like the one in this video, you know how to create it and also how to make it secure. I hope the video was useful. Thank you.